Our last type of proof references sequences. So before we can move forward learning about our last type of proof, we need to learn about sequences. So what is a sequence? A sequence is a function whose domain is either all of the integers between two given integers or all the integers greater than or equal to a given integer. And typically we represent a sequence with a set of elements written in a row. So here we have a sub m plus 1, a sub m plus 2, all the way up to a sub n. Each individual element a sub k is called a term in the sequence, and the k in a sub k is called its subscript or index. M is a subscript of the initial term here. In the example I gave, oftentimes this m will be 0 or 1. We'll usually start with either a naught or a 1. N in this case is a subscript of the final term. So what does our notation tell us? Well, in that specific sequence, we had a beginning and an end. We had an a sub m at the beginning all the way up to an a sub n at the end. But what happens if we have an infinite sequence, or a sequence that never ends? Well, then we have a sub m plus 1, a sub m plus 2 as usual, but then we have this ellipsis to tell us then that our sequence never ends. This is an infinite sequence. And sometimes we can actually find an explicit formula for a sequence, which is a rule that shows how the values of a sub k depend on k. So let's look at an example of what one of those might be and how we use it. So here we have an explicit formula, a sub k equals k over k plus 1 for k greater than or equal to 1. And we want to find the first 5 terms in the sequence. So for our first term, we're going to let k equal 1. If that's the case, we get a sub 1 equaling 1 over 1 plus 1. Literally anywhere that I have a k, I substitute in the number 1. Or in this case, I get a sub 1 equals 1/2. If I let k equal 2, I get a sub 2, which is now 2 over 2 plus 1, or 2/3. If I let k equal 3, I get a sub 3 equals 3 over 3 plus 1, which is 3/4. K equals 4 will give me a sub 4, which is 4 over 4 plus 1, which is 4/5. And finally, k equals 5 will give us a sub 5, which is 5 over 5 plus 1, which is 5 over 6. Not terrible at all. You may have even seen sequences done in another class, particularly those of you who've already done Calculus 2. We spent a lot of time on sequences and series in that class. If you haven't gotten there yet, be prepared. You'll spend a lot of time on sequences and series. So do you think if I were to write b sub I is equal to I minus 1 over I, for I greater than or equal to 2, do you think that sequence is going to be different? Well, let's try it and find out. Let's see here, when I equals, well, this one starts at 2. So here now we'll say I equals 2. We get b2 equals 2 minus 1 over 2, or 1/2. At I equals 3, when we go up by 1, we iterate by 1, we go up to b, or I equals 3, we get b sub 3 is now 3 minus 1 over 3, or 2/3. I equals 4 is going to give us b sub 4, which is going to be 4 minus 1 over 4, or 3 over 4. I equals 5 is going to give us b sub 5, equaling 5 minus 1 over 5, or 4/5. And I equals 6 is going to give us b sub 6, which is 6 minus 1 over 6, which is 5 over 6. So we get the same terms with just a different index. And in fact, we'll find out that there's a way that we can shift from one to the other. But that's in another slide or two. Sometimes we might be given a sequence of numbers here. We have positive and negative integers. We might be asked to find the explicit formula. So here, this is kind of like those brain teaser types of problems you did in math class when you were probably in like elementary school and middle school, where they said find the pattern and you had to figure out what the pattern of the numbers was. Ours is a little more complicated, but we can still make it work. So let's start with lining up our numbers here. We have -6, 12, -24, 48, and -96. So we know already the -6 is going to be a -1 in there somewhere. We just have to figure out where. So if we just start with, let's just say -1 times 6. Because we also notice that every one of these is a multiple of 6. So let's see here. Let's look at 12. That would be 2 times 6. 24, -24, sorry, is a -24 or -4 times 6. 48 is 6 times 8, so 8 times 6, and -96 would be -16 times 6. Well, I have a feeling there's a way we can write this out one more time. Well, here we get -1 times 6. Here we get 2 times 6, and we're going to come back. There might be a little more we add to that one. -4 times 6 is actually a -1, right? Times a power of 2, which is 2 squared, times 6. 8 is 2 cubed times 6. And -16, we have a -1 times 2 to the 4th times 6. So we can already start to see this pattern of 2, 2 to the 2nd, 2 to the 3rd, 2 to the 4th. Well, this 2 that doesn't have a superscript here, an exponent, is just 2 to the 1. And before you say there isn't one for the first term, what about 2 to the 0? It's just 1. So every one of these terms has a 2 to a power. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. We also notice that we have this alternating sign, negative, positive, negative, positive, negative. Well, chances are what happened here is we had a positive one here. We have a positive one here. And here's the other cool thing we know is that here we might have -1 to an odd power to keep it negative times 6 times 2 to the 0. To make that -1 into a positive one, we just need to raise it to an even power here. Times 2 to the 1 times 6. We're back to a negative, so we get to an odd times 2 squared times 6. Then we're back to an even times 2 cubed times 6. And then once more back to the odd to get that negative again. So this is where we can choose our k in different ways. We could split the 6 up into 2 times 3, and then we would add another power of 2 to every one of those 2's. We would end up with 3 times 2 to the 1, 3 times 2 to the 2, 3 times 2 to the 3. All of these powers of 2 would go up by 1 if I pulled the 2 out of the 6. That's one way to look at it. Another way to say this is the 6 is never changing, so let's just leave it there. So we know in our final formula, we want to keep the 6. So we know we're going to have a -1 to some power, and we know we're going to have a 6, and we're going to have a power of 2. Now the question is, how do I know what the power is for the -1 and the 2? Well, that comes down to what do you want to set as your index? Do you want to set k to start at 0? Do you want to set k to start at 1? You can do either one, and neither one is more correct than the other. But what we need to take into account is here we need an odd exponent and a 0. We need it, which is even. We need an even and an odd and an even, odd, even. So what we can do is say, okay, let's try then. What if we said, okay, let's make this k equal to 0 to match the power of the 2. Well, then this power would have to be 0 plus 1 for that one to be 0. And that works. If we let k equal 1 here, we get our 2 to the 1, but our even has to be 1 plus 1. And for the third one, we have k equal to 2. So that would be 2 to the 2. But our odd power would need to be 2 plus 1 or 2 minus 1. But we've been doing plus 1 the entire time. So let's do plus 1. And then the next one, we would have k equals 3. And the last one, we have k equals 4. And in the same way, we have 2 to the third, 2 to the fourth, and each of the ones has an exponent that is 1 more than the index. So 3 plus 1 and 4 plus 1. So this can help us generalize our formula to say, okay, if we call this a sub k, we know we have negative 1, and it's going to be raised to a power. We know we have a 6, we know we have a 2, and we know that when k is 0, I added 1. When k is 1, I added 1. When k is 2, I added 1. When k is 3, I added 1. And when k is 4, I added 1. So every time I have a power on my negative 1, I'm taking that index k and I'm adding 1. But then the nice other side effect is that 2 is to the k, right? 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. So in this case, I have 2 to the k. So my explicit formula says that a sub k is equal to negative 1 to the k plus 1 times 6 times 2 to the k. So what if we wanted to add up all of the terms in our sequence? Well, that has a special name too. That's called a summation. And that's what we're looking at next. So this is a summation. So in 1772, the French mathematician Joseph Lagrange introduced the capital Greek letter sigma to denote summation. And what it means is add everything up after the sigma. So in this case, what does ours look like? Well, we say if m and n are integers, where m is less than or equal to n, the symbol of the sum from k equals m to n of a sub k is the sum of all the terms a sub m plus 1, a sub m plus 2, all the way up to a sub n. So if we were to expand what that looks like, and funny enough, we call it expanded form, not a surprise. When we look at our expanded form, we would say then, let's add each of those terms, a sub m plus a sub m plus 1, plus a sub m plus 2, plus all the way up to a sub n. And we can rewrite it then as one big summation here, where we say our sum from k equals m to n of a sub k is equal to a sub m plus a sub m plus 1 plus a sub m plus 2 plus a sub m plus 3 all the way up to a sub n. And we call k our index of the summation, with m being the lower limit and n being the upper limit. And we're going to find a few summations using these ideas. So if we wanted to compute the sum from k equals 1 to 5 of 2k squared, well, that would be 2 times 1 squared, that's our k equals 1, plus, now add the k equals 2 terms, 2 times 2 squared, plus 2 times 3 squared, plus 2 times 4 squared, plus 2 times 5 squared. And when we do that, we get 2 times 1 squared is just 1, so that's 2. 2 squared is 4. 4 times 2 is 8. 3 squared is 9 times 2 is 18. 4 squared is 16 times 2 is 32. And 5 squared is 25 times 2 is 50. If we add these all up, 8 plus 2 is 10. 18 and 32 is 50. So we get, and another 50 gives us 110. Sometimes all we want to do is just write our summation in an expanded form, though. So if we were to look at example 5.1.4, we want to write the sum from I equals 1 to n of negative 1 to the I over I plus 1. Well, this sum from I equals 1 to n of negative 1 to the I over I plus 1 can be written as, well, drop in I equals 1, negative 1 to the 1 over 1 plus 1. Add to it I equals 2, negative 1 to the 2 over 2 plus 1, plus negative 1 to the 3 over 3 plus 1, plus dot, 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 all the way out to the last term, which would be, in this case, it stops at n. So we're just going to evaluate the expression after the summation with n plugged in. So it would be negative 1 to the n over n plus 1. So if we were to simplify this, we would get negative 1 over 2 plus 1 over 3 minus 1 over 4. And then we would see plus 1 over 5, etc., etc. So plus dot, 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 plus negative 1 to the n over n plus 1. Summations come with their own special set of properties too. So here are some of our basic properties. If we have a sum of a sub k plus a sum of b sub k, if they have the same lower and upper limits, then we can just add them up together in one summation. And if we have c times a sub k and it's summed up, we can remove the c to the outside. So what does this look like if we want to apply it to a problem? Well, in example 5.1.5, I asked you to simplify to a single summation 3 times the sum from k equals 1 to n of 2k minus 3 plus the sum from k equals 1 to n of 4 minus 5k. So all we're really doing is using some of these properties in reverse. So we're going to take this 3, bring it back in, and then we'll be able to add up the two sums because they have the same lower and upper limits. They both go from k equals 1 to n. So we can bring in the 3 times 2k minus 3, and then we can add to it the 4 minus 5k. And the thing is, you have to remember to put parentheses around everything that you're summing. Otherwise, the notation means you're just summing the first term that it's closest to. So here, this means that we have the sum from k equals 1 to n of 6k minus 9 plus 4 minus 5k, or the sum from k equals 1 to n. 6k minus 5k is just k, negative 9 plus 4 is minus 5. So not so bad, it's the sum from k equals 1 to n of k minus 5. And now we've taken what looked like a pretty complicated problem and we simplified it quite a bit. So let's try it again. Now, let's look at 2 times the sum from k equals 1 to n of 4k squared minus 1 plus 5 times the sum from k equals 1 to n of 2k squared plus 1. So much in the same way that we did on the last one, we'll bring the 2 in to the first summation and the 5 into the second. So we end up with one big sum from k equals 1 to n of 2 times 4k squared minus 1 plus 5 times 2k squared plus 1. Or the sum from k equals 1 to n of 8k squared minus 2 plus 10k squared plus 5, which when we put all of our like terms together gives us 8k squared plus 10k squared is 18k squared. Negative 2 plus 5 gives us a plus 3. Much, much simpler. So what happens if they don't have? What if we have two summations and we're trying to combine them, but they don't have the same limits? Well, that's when separating terms comes into play, or something that we're going to learn on the next page, the next slide, called shifting the index is going to become handy. So for this one, we're looking at one sum that's going from k equals 0 to 6, and the other sum is going from k equals 1 to 7. So they have different lower limits and different upper limits. So sometimes we have to pull out a term to adjust the sequence. So if we focus first on the first term, I can adjust that k equals 0 up to 1, but I can't adjust the k equals 1 back down to 0 for the second summation. So here, I can adjust the k equals 0 to k equals 1 by pulling out the k equals 0 term, which would be 1 over 0 plus 1. This is my k equals 0 term. And then I can say, oh, well, now I can add up the rest of the sum from k equals 1 to 6 of 1 over k plus 1. So now I've adjusted my lower limit up to 1. So let's see how that affects the second one and what we need to do to that one. Well, the nice part here is that we've got k equals 1 on the bottom already. So we've got our lower limit is already k equals 1, but we need it to stop at 6. So we're going to go ahead and write it at 6, and then we're going to add to it the k equals 7 term, which would be 7 minus 1 over 7, where this is our k equals 7 term. So essentially we pulled a first term out of the first summation and a last term out of the last summation, but now we have these two summations that have the same lower limit and the same upper limit, so we can put these together. So what happens when we do that? We end up with 1 over 0 plus 1 is 1 over 1, so we just get 1. And I have to bring that k equals 7 term back here. 7 minus 1 is 6 over 7. I'm just going to put those two like terms together. And then we're going to add to it this sum from k equals 1 to 6 of, well, 1 over k plus 1 plus k minus 1 over k. And this is where things get really funky, because now we end up with 13 over 7 for the sum of the first two terms. And we have to find a common denominator for the inside. K and k plus 1 don't have anything in common, so our common denominator is going to be k times k plus 1. So I'm going to have to multiply the first term by k, and the second term, that k minus 1, by k plus 1. And this looks really complicated. But what happens if we add all this up is it equals the number 7. Now notice we've got 13 over 7 plus a sum from 1 to 6 of k, plus k minus 1 times k plus 1 over k times k plus 1. This is not an uncomplicated summation. We didn't do anything wrong, but it's still really complicated. Something some of you may have noticed is that if k equals 0 to 6 here, we have the 0, 1, 2, 3, 4, 5, and 6 terms, which is actually a total of 7 terms. The second summation here goes from 1 to 7, which is 1, 2, 3, 4, 5, 6, 7 terms. So they actually have the same number of terms. So there's a way we can adjust one of these summations to actually have the same index values, the same index limits as the other. And we're going to do that on the next slide. So we're going to transform the first summation, the 0 to 6. We're going to transform it to starting our lower limit at 1 instead of 0. So how can we do that? We call this a change of variable. So it's called a change of variable. And the way we're going to do that is we're going to let j equal, well, what do I want to do to k? I want to raise it by 1. I want to raise that 0 to a 1. So if I let j equal k plus 1, then I can solve for k. Then k is equal to j minus 1. And now plug it in. So what that gives us then is a sum from k, which is now j minus 1 equals 0, to k equals 6, which is now j minus 1 equals 6, of 1 over k, which is now j minus 1 plus 1. So hopefully you can see this is already starting to get less complicated, because now we're going to have a sum, add those ones to the other side, of j equals 1 to j equals 7, of 1 over, well, j minus 1 plus 1 is just j. And now we've adjusted this to being 1 to 7 instead of 0 to 6. Here's the super cool part of this one. The name of the index does not matter. So let's let j equal k again. So we'll just send it back. Then what do we have? We have the sum, now j is just k again, of k equals 1 to k equals 7 of 1 over k. We have just shifted our index. That's what this is called. This is called shifting the index. For those of you that have to do Calc 2 and differential equations, you're going to be doing this particularly a lot in differential equations. You do a whole lot of shifting the indices when you're looking at power series solutions to differential equations. In particular, higher order differentials, and it helps a lot with nonlinear higher order differentials that you can't solve by other means. So let's see if this one can help us reformulate that summation from the first page. So we're going to remind ourselves that we shifted this to k equals 1 to 7 of 1 over k. And we're going to now be able to combine them as is, because we shifted that first one to k equals 1 to 7 of 1 over k, and we're going to add to it the sum from k equals 1 to 7 of k minus 1 over k. And what happens is now we have the sum from k equals 1 to 7 of 1 over k plus k minus 1 over k. They have the same denominator, so all we have to do is add the numerators. So we get 1 plus k and minus 1 all over k. Or the sum from k equals 1 to 7 of k over k. Well, we just got the sum from k equals 1 to 7 of 1. That's literally 1 plus 1 plus 1. That's 1, 2, 3, 4, 5, 6, and 7. We literally just added up 7 ones. This is the heart of at the heart of the program that I told you guys about that I gave my other class at the other school. I gave them a project on something very similar where I had them take these summations, which are, I hope you've realized by now, the same as loops. And when you shift the index, you should get a simpler formula to have to plug your loop values into. So it should take less computing time. So it should take less processing time, computing time, and overall algorithm time to be able to run those computations, particularly when you're looking at large summations, 10,000, 20,000, a million values that you're summing. So it works out really well. And sometimes the question I get asked on this one is, could I have also shifted the 1 to 7 term down to 0 to 6? Absolutely. So we could have shifted, if we wanted to shift the k equals 1 to 7 term, k minus 1 over k, if we had wanted to shift that one down to 0 to 6, we could have shifted that to k equals 0 to 6 of k over k plus 1. And I will leave that one to you to figure out how. But I'll give you a hint. Let j equal, well, you wanted to shift the k from 1 down to 0, so you wanted to take 1 away from k. And you should be able to figure that one out. And then what happens is, when you put them together, you still end up with a summation of 1 from 0 to 6, which is still 7. One last notation that you probably haven't seen before in this section is this large pi. So we had a Greek symbol for a summation of a sequence, but what happens if we want to look at a product of a sequence? Well, enter the large pi. So if we have m and n that are integers, where m is less than or equal to n, the symbol of the pi with k equals m at the bottom and n at the top of a sub k is the product of all of the terms a sub m plus 1, a sub m plus 2, a sub m plus 3, all the way up to a sub n. So we would write it in its expanded form, right, as a sub k equaling a sub m times a sub m plus 1 times a sub m plus 2 times all the way out to a sub n. And these products have similar properties to the ones that we looked at for summations. But in particular, this one only has the multiplicative property. If they have the same lower and upper limits, two products, you can then do one product of their product. That's a whole lot of saying product. You can take a sub k times b sub k and do one product. So what does it look like to evaluate one of these products? Example 5.1.10 asks us to compute the product from k equals 1 to 5 of k. Well, that means we've got k equals 1 is just 1 times k equals 2 is 2, 3, 4, and 5. So this is it's 120, but another name for this is also 5 factorial. So we're going to learn about that on the next page. It means you multiply every number up to that value. So we're going to learn about that on the last page. But some of you will have recognized that as a 5 factorial. How about if we wanted to compute the product from k equals 1 to 3 of k over k plus 2? So I made it a little more complicated this time. But when I plug in 1, I get 1 over 1 plus 2 times, now plug in 2. 2 over 2 plus 2 times, and the last one we have to plug in is 3. So 3 over 3 plus 2. or 1 over 3 times 2 over 4 times 3 over 5, which is 6 over 60, or 1 over 10. And the last example using the product notation is the product of two products that have the same lower and upper limit. So this is one of those ones where we can use that property where we make this just one big product from k equals 1 to 3 of k squared times k over k plus 1. Or the big product here, sorry, big pi, so the product of k equals 1 to 3 of k cubed over k plus 1. So what does that look like? Well, we only have 3 terms. It's 1 cubed over 1 plus 1 times 2 cubed over 2 plus 1 times 3 cubed over 3 plus 1, or 1 over 2 times 8 over 3 times 27 over 3. Oops, sorry, over 4. So we end up in the end with 9. I mentioned the factorial on the last page, and it's a property of numbers that comes up so often that we gave it its own symbol and its own name. In particular, it comes up a lot in probability and probability theory, combinatorics, those sorts of things, counting. If you've ever done a problem that asks you, there are 5 white balls and 4 green balls and 3 blue balls in this urn, reach in and pull one out. What is the probability that it's blue? That's an example of a combinatoric type question. And that might involve things like n choose r, which we're going to talk about at the bottom of the page, and factorials. So sometimes when you get into programming, you find that you're going to have to apply factorials or n choose r. So we're going to go through those concepts here. So a factorial, like I showed you on the last page, it looks like an exclamation point. So n factorial is 1 times 2 times 3 times all the way up to n. So a special note here, by the way, something you really need to take special note of is that 0 factorial is just 1. So let's find 4 factorial. 4 factorial is going to be 1 times 2 times 3 times 4, or 12 times 2 is 24. What about 9 factorial over 8 factorial? Well, that would be 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 and times 9 over 1 times 2 times 3 times 4 times 5 times 6 times 7 and times 8. This is where the 1s, 2s, 3s, 4s, 5s, 6s, 7s, and 8s all cancel, and all we're left with is 9. So what do you think that n plus 1 factorial over n factorial is going to look like? Well, think about it. That's like 9 factorial over 8 factorial. We just had 9 left. Well, this would be 1 times 2 times 3 times all the way up to n minus 1 and n plus 1. Over n factorial is going to be 1 times 2 times 3 times all the way up to n minus 1 and n. And here, everything's going to cancel out now, except for n minus 1. Oh, sorry, n plus 1. So we're left with just n plus 1. So the last topic of interest here with counting and probability applications is this concept of n choose r. Sometimes you need to find the number of combinations possible given a specific situation. And needing to know that number of combinations involves factorials, which is why we looked at factorials above. So if we have n items and we want to choose r of them, that formula is n factorial over r factorial times n minus r factorial. So if we have 8 choose 5, then we have 8 factorial over 5 factorial times 8 minus 5 factorial, or 8 factorial over 5 factorial times 3 factorial. So if we write it out, we have 1 times 2 times 3 times 4 times 5 times 6 times 7 and times 8 over 1 times 2 times 3 times 4 times 5 times 1 times 2 and times 3. When we start trying to cancel 1s, 2s, 3s, 4s, and 5s, but 2 times 3 is also 6. So 1, 2, 3 is 6. And we're literally left with just 7 times 8 here, which is 56. So there are 56 possible combinations of size 5 given a set of 8 objects. 56 different combinations. So let's try, like we did before, we did n plus 1 factorial over n. What if we say, now let's try finding n plus 1 choose n? 5 choose 4, 10 choose 9, right? How many ways are there to choose one fewer object than the set holds? Well, let's see. We get n plus 1 factorial over n factorial times n minus r, right? So in this case, n plus 1 minus n factorial. So we get n plus 1 factorial over n factorial times 1 factorial. And 1 factorial is just 1, so we get n plus 1 factorial over n factorial, which we just found out up there was n plus 1.